Greetings and welcome to the Introduction to Astronomy. In this episode of New Discoveries in Astronomy, we will talk about how astronomers are using artificial intelligence to better understand how neutron star mergers create many of the universe's heaviest elements. So let's get started. How do astronomers know where many of the universe's heaviest elements come from? Elements such as gold, platinum, and uranium were not created during the Big Bang. Instead, they formed much later during some of the most violent events in the universe. One of the most important of these events occurs when two neutron stars collide. These extraordinary mergers not only produce gravitational waves and brilliant explosions called kilonovae, they also create many of the heavy elements that eventually become part of planets, rocks, and even ourselves. Creating heavy elements requires an enormous supply of free neutrons. During a neutron star merger, atomic nuclei rapidly capture these neutrons through a process known as the rapid neutron capture process, or R process. As neutrons are added, some transform into protons, allowing the nuclei to grow into progressively heavier elements. This chain of nuclear reactions occurs incredibly quickly and involves thousands of unstable atomic nuclei. Understanding exactly how these reactions unfold is one of the major challenges in modern nuclear astrophysics. Modeling the R process requires scientists to calculate enormous numbers of nuclear reactions occurring almost simultaneously. Each reaction releases energy that influences how matter is ejected from the merger and how bright the resulting kilonova becomes. Traditional simulations attempt to calculate every reaction in detail. While highly accurate, these calculations demand tremendous computing power and often require simplifying assumptions. Researchers wanted a way to preserve the underlying physics while making the simulations much more efficient. To solve this problem, researchers developed a machine learning model called RHINE. Rather than replacing the physics, the system first learns from thousands of detailed nuclear reaction calculations. Once trained, it can accurately estimate how much energy is released during the R process while the simulation is running. This dramatically reduces the amount of computation required while maintaining excellent agreement with the full nuclear calculations. The result is a much faster way to model how neutron star mergers evolve and produce heavy elements. Better simulations allow astronomers to make more accurate predictions about neutron star mergers and the light they produce. Those predictions can then be compared with observations from telescopes and gravitational wave detectors. At the same time, laboratory experiments that study exotic atomic nuclei provide important data that improve the models even further. Together, observations, experiments, and simulations help scientists build an increasingly complete picture of how the universe creates its heaviest elements. Every atom of gold, platinum, and many other heavy elements has a remarkable cosmic history. By combining nuclear physics, astronomical observations, and artificial intelligence, scientists are learning to reconstruct that history with ever greater accuracy. Each improvement in our models brings us one step closer to understanding how some of the universe's most extraordinary events shaped the matter that surrounds us today. So that concludes our discussion on how AI maps the birth of heavy elements. We'll be back again next time for another new discovery in astronomy. So until then, have a great day, everyone, and I will see you in class.